Welcome to those who are joining us this evening for the Water and Environment Society of Engineers Ireland for the first webinar of the 2025-2026 season. My name is Kevin Murray and I'm a committee member of the Water and Environment Society and a technical manager with EngineersIreland and a fellow of Engineers Ireland. And can I just say on behalf of the Water and Environment Society of Engineers Ireland, we're always welcoming new members, members that are interested in participating in the committee, and members that are interested perhaps in presenting topics of interest to the members of the society. So don't be shy about getting in contact with us through our secretary there, Justin Waples, who's also on this call. While I have your attention, please do keep an eye out for future events that will come through the circulars. Let me begin by introducing you to our speaker. And Kristin Eklöf. Kristin Eklöf is a data scientist and founder of salbo.ai, which is specializing in advanced analytics and artificial intelligence, where it is applied to transportation, infrastructure, and construction. And Kristin has over a decade of experience in this area and has been working on national road maintenance policy in Sweden and decision support systems for Network Rail in the UK, and also working in transmission line construction in North America. So a global experience. And in this presentation, Kristin is going to introduce to us the data-driven approach to the maintenance of municipal roads that is based upon real-time information coming in from connected vehicles right across Europe. So this is where your vehicle is sending back data to the cloud, and if you wonder where it goes and what it's being used for, well, I would hope we'll learn in this evening. So I would now open the floor to Kristin to give her presentation this evening. Thank you very much.
Thank you so much, Kevin. It's a pleasure to be here and present to you. So as Kevin mentioned, I've been working in this field for quite some time. I did my master's thesis and my PhD dissertation predicting lifetimes of asphalt payments using data. And that was data from a national database we have here in Sweden, a huge database on the national road network. And since I expect that not all people in this webinar listening to this presentation are road people, I wanted to start by giving a short, brief overview of road maintenance and payment management planning. And here in Sweden, and I expecting in many other countries too, the road network is divided in different levels. And on a national level, for the national roads, there's a data-driven payment management program in place. There are condition measurement data collected annually, and Sweden have been doing this since 1987, which happened to be the year I was born, so I always remember that year. And when I, as a master's student, encountered that database with payment maintenance treatments and condition data, I was floored by how much data there were to analyze. And this I think is common for national road agencies. But when we look at lower levels of the road network, so for example, municipal roads, city roads, that's not at all the case. There might be no data at all, basically. And a lot of municipalities, including the one I'm going to use as an example here today, a Swedish municipality, the best case scenario is usually that they do a visual inspection of the road network maybe every 5th year. This is what this municipality did. And then they go out and based on that assessment, they will go out and fix the roads, the worst roads that they see in that assessment. Sometimes the data is stored, sometimes it's not. Some municipalities and cities, they don't have an inspection at all. They just, you get a little bit of money and then you go out and fix whatever you feel you can afford. You maybe drive around and see something and do that. So it's not as mature as the national program, and this is valid because of course municipalities don't have the same resources, and to do the traditional condition assessments with lasers, and you have the specific vehicles that drive around, they are expensive. Like it's just not feasible for smaller communities. So in this project, I started to explore connected vehicle data, as Kevin mentioned, because that's data collected from vehicles already on the roads, and it's a lot more accessible, and it's also a lot cheaper for cities. So can we use that data for municipal maintenance planning? And also, I'm also going to demonstrate the value of going from this ad hoc worst first type of way to maintain your road network to a data-driven structured maintenance plan. And I'm going to show you that it's efficient from a financial perspective, but it's also good for the environment, and you will significantly decrease, or cities can significantly decrease their greenhouse gas emissions by going from worst first to a more proactive payment management strategy. But I'm going to start by talking a little bit about connected vehicle data, because this is of course the new maybe a little bit fun part of this project. Some parts of it is very traditional asset management principles combined with this new hyped data source. And of course, cars nowadays are basically moving sensors. And this particular data that I use come from the Volkswagen Group and a company called Naira Dynamics. So they are compiling data from the Volkswagen Group's fleet. So that includes Volkswagen itself, but also Audi, Skoda, Porsche. And the data comes from the tire grip software that the cars are equipped with. So it's a, you could call it a residual product of the fact that your car will warn you when you have a low tire pressure. So the engineers at Naira realized that, well, this is not only showing us the tire pressure, it's also showing us the tire's interaction with the road surface. So they developed two different products. One is friction, which can be used for winter maintenance, and the other one is roughness. And the roughness is the indicator that I used. And I think this slide was created a couple of years ago. So they had 2 million vehicles live that are sending data to the cloud continuously every hour. I think there might be actually more than 2 million vehicles now. And the data is processed, and then the measurements, or these two indicators, frictions and roughness, is what's being sent back to me in this case. And it's completely anonymized, and when you allow your car, you as an owner will agree to send data, and when you agree to that, this is what happens with the data. So I don't know which specific car the data comes from. I never know that. I only know it's at an aggregated level. So what does this data look like? So roughness is measured, it's correlated with a standardized roughness measurement, which is called International Roughness Index, IRI. It's measured in millimeters per meter or meters per kilometers, and it's basically an indicator showing how smooth it is to drive on the road. So a low IRI value is somewhere around 1, and a high value is somewhere 5, 6, 7, 8, and it's starting to become really rough. And the data points you see here on the screen right now shows weekly averages. So I've aggregated daily measurements to weekly averages for a few different, 6 different sections, road sections in a Swedish municipality. And And this data exhibits, it has some interesting features, especially when it comes to variation and behavior for different types of roads. So for this pink points from the pink section, you can see that there's a lot of variation week to week. One week it's down at 3.8, something like that. And then next week or a few weeks later, it's almost 7. So there's a lot of weekly of variation in this from this for this section. And I will explain a little bit later why that happens. While this blue dots, which is from a different section, is there's a little bit of variation, but it's in a very narrow range. It has a very static behavior, almost stationary, not much change from week to week. So it's in comparison to traditional data where I have one measurement. I usually measure the Swedish Transport Administration measure the national road network once per year. Here I have weekly measurements, but also a lot of variation. So that's a little bit of a challenge when I'm gonna try to create a maintenance plan based on this data. Another thing I do when I collect this data is that I exclude winter. And this will be a little bit different for different places, but this particular municipality is close to Stockholm, Sweden's capital. I will show you on a map later. So I've excluded data points from November to March because it will snow. And when it snows, the road, of course, gets rough, but it's not because of the pavement quality, it's because of snow. So I don't want that data to bias my analysis. If I'm further north, I might need to exclude April and October as well, because snow can fall earlier. So that's one thing I do here. And then another challenge is that the number of measurements varies a lot too. So for this, again, this blue section, I have a point every single week. So for this municipality, sometimes I have thousands of measurements per year, meaning I have thousands of Volkswagen cars driving on that road section every year. And then sometimes, like this green little road section, I only had one measurement in 2022 for this road, and then I had 2 in 2023. So maybe this is a local street, or it could be a local street where nobody owns a Volkswagen car. And then in the middle of the summer, grandma comes by and she owns an Audi, and then suddenly I have a measurement. But of course, I only have one data point that year. So there's less data to, I can't be as sure what the actual condition is, especially if I have a lot of variation, as we see in the pink, on the pink road. So that's also a little bit of a challenge. But because I have this continuous collection, I pretty quickly accumulate a lot of data, and I can use it to try to predict the condition of different road sections. So for example, for a road in good condition, these are 3 different road sections that are all in good condition. And why do I say that they are in good condition? It's because the roughness is consistently low. And for the red road here, we can actually see a drop here during 2022. It was up here, and then boom, it's getting better. It was it was probably a maintenance treatment that happened here, which I can see in the data. So these are roads in good condition with pretty consistent behavior. So in 2024, they were all in good condition. I can also use this data, of course, to classify which roads are in poor condition. And the way I do that is, of course, looking at the roughness. So like I said, when something is starting to hit 6 or something higher, then it's pretty rough to drive there. But another very prominent feature for roads in poor condition is actually the variation. So I can also use the fact that there's a lot of variation. Why is there a lot of variation on poor roads? Well, the driver behavior will impact my data collection. So some people, when a road is very rough and has maybe a lot of potholes, stuff like that, they will drive slow and be very cautious. They will not drive over the potholes. Some people just don't care and they drive over everything. So it's very typical to see that adjustment and to have a lot of variation for poor roads, while good roads have very little variation. So that's also one way to distinguish. But overall, the condition of these 3 roads is classified as poor. I can also identify maintenance treatments happening in this data, like you saw here for the good roads. This is a similar thing happening. It will look a little bit different, but like you see here for the brown and sort of purple road here, I had a lot of variation, and then in 2024, I still have some variation, but it's at a lower level and it's less. So that's also one way to like, okay, something probably happened here. And it doesn't necessarily have to be that these roads were poor or had a maintenance treatment happening because the payment was bad. It could also be construction going on. And then from one year to another, you actually, you're fixing the pipes, for example. And the road, so it will be rough to drive on that road, and then the asphalt is restored, and then the road looks good again. But for the green road here, I would say it was probably pavement maintenance, because it had gotten significant or a little bit worse every year, and then a significant drop. And then finally, I can look at the deterioration patterns over time, which will also look a little bit different. So for sort of the turquoise road here, we can see, well, over time, it's sort of, this was the condition 2021, this is the condition 2024. So it has deteriorated or became, yeah, we have a clear deterioration pattern here. And then for the roads with more variance, it's obvious when you see it over time. The variation gets higher, and also we are sort of oscillating on a higher level of roughness. So I can trace the deterioration pattern over time, even though I have this inherent variation. When I do the long-term maintenance plan, so which is a program for which roads will have new asphalt pavement over 3, 5, 10 years, I wanted to standardize, or I needed to standardize this roughness, because it's not just roughness that matters, it's also what type of road it is. So the predicted condition is important, but so is the speed, because if I have a lower speed limit, I can allow more roughness. And if I have a higher speed limit, the road needs to be smoother to be safe to drive on. And then finally, the traffic matters too. So if I have a lot of traffic and high speed, I want smoother roads. This is also an economic decision somehow. Like more traffic will mean more people drive on smoother roads. If you have a local road where 3 people live, maybe they can endure a little bit of roughness a little bit longer than on your main road in your city. So I'm using these indicators to classify roads into an index. And this is also for visual purposes, because roughness is a very technical measurement. And if you're presenting to your city council or politicians, they will lose, you will lose their attention quickly. So I've standardized the condition, the roughness into a condition index based on the predicted conditions. And then I have different standards for speed and traffic, like I said. So high speed roads with a lot of traffic, I have a higher requirement or they can not be as rough as a low traffic road. And then the roads are classified into 5 different classes, and they all get an index value based on how close they are to a benchmark value that I've sort of picked or try to compare with what the national standards say. So the Swedish Transport Administration has a maintenance standard that says that if a road has this amount of traffic and the speed limit, we don't want roughness higher than this specific value. So that's how I standardized the roughness against to create the index. And then they are classified just excellent, good, fair, poor, very poor. So what does this look like in an actual city? My example is a municipality called Nacka. It's located just outside of Stockholm. And as you can see, this is, well, at the latitude of maybe northern Scotland. So everything is north of Ireland, but from a Swedish context, we're still in the south of Sweden. So it's not the worst winters, but still absolutely winter. Nacka has about a population of like 100,000. It's a pretty diverse municipality. So to the left is a picture of high rise in a place called Fisksätra in Nacka. This is a high rise from something that Sweden did in the 1960s and 70s, where the Swedish government decided to build 1 million homes in 10 years. So we call it the Million Home Project. They are usually more socioeconomic disadvantaged, these areas. And then we have in Nacka some very posh areas. This is from a place called Salbo. This is a very famous hotel. So I would expect that I have some data points collected by Porsches from people living here. So we have some very like fancy neighborhoods. And then because it's so close to Stockholm, the capital, we also have some very like newly constructed urban city centers where, new constructions are happening. Nacka is soon getting subway line. They don't have it yet, but it's being constructed. So there's a lot of construction and expansion going on. So it's a pretty diverse municipality in that sense. So what does a payment management program in Nacka look like based on connected vehicle data? Well, when I do this, I need to combine, or I'm combining a few different things. First of all, is the condition. This is what the condition assessment looked like using the roughness and then translated to the index. So I have quite a lot of red streets around. I also have some green, which is in good or excellent condition. But condition is not the only factor I want to use when I create the payment management plan. I'm also interested in the criticality of the different roads. And with that, I mean, some roads are just local streets leading to a few people's homes. Some roads are main roads where that a lot of people use to commute. And this specific map that I'm showing now actually shows the bus network, so public transport network, which is how a lot of people get to work, how kids get to school. And this criticality map does not distinguish between socioeconomic areas. It's just where do we have the public transport. And this is how Nacka wants to prioritize their payment maintenance. These are the most critical roads in their community. And then these two maps are combined into a risk assessment. And if we look at this one, it's actually pretty green. There's a meaning that there are not a lot of high criticality streets in poor condition, which is a good thing. But there are some portions of the main road here that are in poor condition. So they should have priority. So already here we can kind of see that this is not about maintaining your worst streets first. This is about combining different objectives. So some people will need to live with maybe having a street in poor condition, depending on the budget. Some people will need to live with having a street in poor condition because it's not a high risk or a critical street. So the budget, of course, determines what type of work I can do and how much I can do. So this first one is maybe to some people, like, why have why have a projection that shows that, well, without maintenance we will have a very, very poor network in 10 years. But it's a good it's good to understand and to visually understand that this is not this is an important, we need to spend money. Swedish municipalities have a lot of responsibilities. They have healthcare, they have schools. So of course, road maintenance isn't on top of everybody's priority, but we need to do maintenance every year to be able to travel at all. Of course, the current budget when we started on this project for Nacka was the equivalent. So Sweden still has the krona, but it's an equivalent of 2.1 million euros per year. And this prediction is based on the deterioration rate that you could see earlier, and of course the cost of maintenance. And Sweden also experienced a lot of high inflation after Russia's invasion of Ukraine. So the cost of asphalt, the cost of fuel, the cost to do anything increased a lot. I think they had, but like increased in cost of like 60% from 2021 to 2023. So that was a lot. The current budget is just not sufficient, as you can see here on this prediction. They can't keep up with the needs. So the roads deteriorate faster than we have budget for. So a sufficient budget would be 3.2 million euros a year. And there are still roads in poor condition with this budget. But the important part here is that I can keep my good roads and my prioritized roads, my public transport network and my main roads in good condition. And then I can slowly start lowering the backlog for my local streets. So that's why I say that this is a sufficient budget. You don't necessarily need to erase your maintenance deficit all in one shot. The important part is that you're not constantly at a deficit and you're not adding to that deficit. So with time, with this budget, they would be able to keep up. And because in this scenario, I'm able to maintain my critical streets, which is the most important part here. We can also look at these two maps, which will show you the difference between a preventive maintenance strategy and the worst first strategy. So both of these maps are projections of or predictions of the condition 2033, which is the original data here is from 2023. So like 10-year outlook. And to the right, you can see that a lot more streets are red, not all of the streets, but a lot more. And that's because to the right here, I'm using the worst first approach. If you remember, that's what cities traditionally have done when they do an occasional assessment or an occasional inspection. And that's because with time, when you do your worst first, your worst roads, especially your worst local roads, will be more expensive to fix than if you apply a preventive maintenance strategy, meaning you make sure to keep your high priority roads and your good roads in good condition with less expensive treatments. So that will give us a better road network in 10 years with the same budget. So with the current budget, even if I can't get a budget increase, I will still have a better road network in 10 years if I have a preventive maintenance strategy and if I use data to drive my decisions rather than go out and ad hoc do my worst streets first. So that's the conclusion here, and we can model that in these maps. So this is, of course, what I want Nacka to do. If we instead look at let's say Nacka they will go to their council and tell the politicians we need more money, and then the politicians are like, okay, tell me, what do you need to like fix the roads or have a more sustainable road maintenance strategy? Well, if Nacka uses the preventive maintenance strategy, the budget they need to tell the council is this 3.2 million, like you saw earlier. That's what That's what they need. This map is actually equivalent in terms of average condition. It's almost the same in terms of not every single street has the same color in these two maps, but almost. If I apply the worst first strategy and I want to obtain a similar condition, I need 4.8 million euros to do that. So it's much more expensive if I start doing my worst streets first, and then when I fix that street, another street is really in really bad, poor condition, and then I need to fix that street. It's more like chasing your own tail approach. So this also matters, of course. How much money do I need? And like I said, this you need to you have a lot of things that needs attention. So of course you don't want to use more money than you actually need. That's why strategy is important. And then finally, which is also very interesting, because now I've just been talking about euros, and of course politicians and a lot of people are very focused on that. But in terms of emissions, we are actually benefiting greatly from using a preventive maintenance strategy as well, because we use less materials, and we also do the maintenance treatments with better timing, which matters. So with preventive maintenance, over 10 years, I have emitted 3,000 metric tons of carbon dioxide equivalents, which is sort of the greenhouse gas emission currency, if you will. And with worst first, I've emitted 6,000 metric tons. So it's quite a difference in terms of it's million tons. So it's quite a difference in emissions as well. And this is all other things equal. I'm using the same equipment, the same materials. It's just a difference in strategy, maintenance strategy. So to summarize, this is the accumulated maintenance cost using a preventive maintenance strategy is 57% lower than if I do the worst first, and the emissions are 89% lower. So that's huge difference. And I should say that especially, so the emission numbers are based on adding or using environmental product declarations, which is how asphalt producers disclose the emissions for the material. And then I've also added the cost of or the emissions for using like the vehicles we need to use to get the material to the municipality, and also the emissions using the equipment to just do the asphalt work. And when you do worst first, you need more material, more equipment. That's actually the difference here. You need a deeper treatment for those roads than you do with preventive maintenance. That was the last slide.
Kristin,
thank you.
Kristin, that was fascinating. Thank you very much.